Okay, today we're talking about statistics, extrapolation, and interpolation. Basically, these are ways to deal with uncertainty in real data and real information. First of all, let me remind you that Excel is very, very important. We've talked to our industrial advisory boards, and they come back and tell us all the time that Microsoft Excel, proficiency and ability with Excel is very, very important in an industrial setting so that you know how to deal with data and deal with Excel spreadsheets. It's pretty much everywhere. It's how engineering people use a lot of data and organize data and visualize data in many cases. So we can't teach you a whole lot. We're just going to give you the basics of Excel. But you need to, if you're very interested, you should learn more about Excel because it will make you a better engineer one day. Back to uncertainty. Why do we look at this? Because there's uncertainty in the real world. So this is a research paper we did looking at particulate granulation, trying to smash particles together to make bigger particles. And uncertainty when we actually do experiments is significant because you have to model the systems. What's the probability of two particles of sizes at certain velocities agglomerating to make a bigger particle? How do we deal with looking at the particles and the average size of the particles, and how do you describe how uncertain that value is? So in real experiments, you can use a bar graph. So in this case, you change the material formulation for different polymers, and then you look at basically the strength of the polymer. Every material, every experiment is going to be different, so you have uncertainty error bars above the bar graph to represent how uncertain the system is. Sometimes we have XY plots. If we have a time response, you can look at something as a function of time, and each point in time you may do 5 or 10 experiments. You have uncertainty to represent how uncertain the data points at that point in time are. Are they, if it's a large error bars and they overlap a lot, it may not be a very interesting response because you can't tell from one group of data to another group of data that they're significantly different. So things we have to master to make sure we're all on the same page: mean versus median, standard deviation versus standard error, interpolation and extrapolation, linear regression, and nonlinear regression. Those are the 4, basically, sort of, I guess 8 things, 4 different things overall, but the 8 topics you need to take home today. Data variability. First of all, in biomedical engineering, our data is going to have lots of variation. So this is sometimes caused by biological processes. If something happens, or just populations, even if you try and raise mice all the same way, they could be different just because of the way evolution or parenting works. You have a combination of a mother and a father. Other external disturbances could affect the process too. Things outside of our control, things that affect the biology outside of the experiment. The patient population varies from one patient to another, and it changes with time as well. So younger is different from older. Limitations in our measurement device. The measurement that you're using to measure things may have some uncertainty. It may be dependent on noise or even ambient temperature. Something that you're not measuring or you don't know could be affecting your device or your population. So these external forces, so basically is another word for disturbance, something outside of your control. Maybe there's something you haven't thought of that's affecting your process that is making it change with time. So variation, disturbances, population variation, measurement device limitations, and external forcing are the main things that push our biomedical engineering systems around that we can't really account for. So we try and just quantify the uncertainty. So given a mean, the median is easy to do. The median is just sort the data, and it's the one in the middle. If you have an even number of data, you average the 2 values in the middle to get the median. Mean, you have to actually take the average. So you should know how to get the average of values by adding them all up and then dividing by the number of values. So this median value is very simple to find. Just arrange them, find the middle one, and average the middle 2. It's not that hard to do mean and median. This should be very remedial. You should have seen this in elementary or middle school, maybe high school, I don't know. Somewhere you've learned how to do median and mean of a data sample. Standard deviation and standard error are more interesting because they tell you about how uncertain or what the variation in your data is around the average value. So the variance is the first thing you have to calculate. Once you have the mean, the average, for each piece of data you find the error and you square it and you divide by n minus 1. Since we don't have the whole population, we're using n minus 1. The standard deviation is related to s squared or sigma squared. The standard deviation is just the square root of this variance. So once you calculate sigma squared or s squared, the standard deviation is just the square root of that value. Very easy. Now the standard error of the mean is sometimes reported. So you find the standard deviation and then divide by the square root of n. So these three values, you should be able to calculate these. You have to know the average and how many data points you have to calculate the variance. It's very easy to get the standard deviation and divide by square root of n to get the standard error. But whenever you're reporting data, you need to say what the value for n is. How many data points do you have? So if you have a lot of data points, you can drive this standard error of the mean to a small value because you're dividing by the square root of n. So that's an honest deception, sometimes exploited. Basically, you need to let people be honest with how much data you have, what those values are. Now, probability distributions. You get more into this in advanced engineering statistics, but generally a lot of systems will obey a normal or Gaussian distribution for a random variable. So the standard deviation and the mean are all the information that you need to describe that uncertain value. So some people go into central limit theorem, basically everything is normal for enough samples. If you look at student grades, for an average of 50 with a standard deviation of 10, if you only sample 40 from a basically a computer MATLAB program, this example shows you it doesn't look like a bell-shaped curve. You can see gaps when you look at this histogram with the frequency of the students scoring for only 40 students. But when you go to n equals 100, n equals 1,000, it's starting to look more like a smooth bell-shaped curve. Even for n equals 1,000, this sample, this random sample with 1,000 samples from that probability distribution doesn't look exactly Gaussian because you have some areas where there's a significant number of samples there. But when you get up to 10,000, that's a lot of student grades. It looks very much like a bell-shaped curve at this point. So it's nice and smooth, and on either end you have no one making 100, no one making 0 because of this standard deviation of 10. What does that mean? The standard deviation of 10, the most important thing to know is for a bell-shaped or a Gaussian curve, a normal distribution, if you have the average plus or minus that standard deviation, will include 68.3% of all the data. You can get into why you can do integrals for that probability distribution to figure out exactly why that is, but effectively for this student example where you have an average of 50 plus or minus 10, everything between 40 and 60 should represent 68.3 of all your data points. And there are other numbers for plus or minus 2 sigma and 3 sigma. I think at 3 sigma you get up to 99% of all your data. Now, something interesting, a lot of people have tried to use statistics to prove things. It's not necessarily a great area, but there are papers. Here's an example of a paper looking at test scores for ASVAB, which is a military testing to see what your capabilities for military are. The males and females in this study were basically the same average, but they had different distributions. So they may, at least in this example data, the males had longer tails on that distribution, which means that in this example, the boys and girls were basically on average the same intellectual ability, but there were more male students on the very high end and more male students on the very low end. So that keeps the average the same, but it spreads out the population. So one of the issues with this is you can't really measure intelligence by one test. This is really just a data point, but on this one it's interesting to see that there's a different distribution in something that you would think would be very, very similar, even though the averages are the same. Another problem we have to deal with is interpolation of data. If you have data and for some reason you need to find the value of f of x between, you have data 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and you need to find the value of this function between these 2 points. The simplest way to do this is linear interpolation. So we're going to use 2 points. We're going to have x equals 4 and x equals 5, and try and find the value at x equals 4.3. So we know it should be somewhere between 63 and 55. So we're going to use linear interpolation for this data. The formula for that is given here. Basically, the function evaluated at the left side, how far away from the left side the x value is, and then the slope, the function value of the right side minus the function value of the left side over the right side minus the left side on the x value. So if you plot the data, you look here and you say, oh, it's 63, and then it goes down to 55. So it should be somewhere lower than 63. If we plot the data, we know what to expect. So we plug these values into the formula. You get the function value, how far away from the left side it is, the slope, and putting this together, you get 60.6, which seems reasonable because it should be somewhere lower than 63. Now, obviously, this data is probably not the best data to be doing interpolation on because some of this data point may be an outlier. But assuming that this is the right data and we want to interpolate between these two values, this is the formula to interpolate between two values when they're a function of x. Now, again, you need to make sure it's between the two function values. Now, if it's closer to one end, the value should also be closer to that end. In this case, our function, we were at 4.3, which is closer to the left side. So we should be closer to 63 than we should be to 55. And we're less than, or 2.5 away from 63, but we're more than 5 away from 55. So that makes sense. It seems like a reasonable answer for interpolation. Extrapolation is another method. You can look at extrapolation when you have limited data and you want to go outside your range. So in this case, if we want to go down to an x value of 0.5 or an x value of 11, that was outside of the data we're given. So again, there are many methods to do this. We're going to do linear extrapolation, which uses the same formula. It just uses it in a different way. So here's another example. We have the same formula. The left side of the range of interest, the x value, minus the left x, and the slope between the 2 points. So for this case, to evaluate f at 11, our left point value is going to be at 9, and our right point value is going to be at 10. So that's where we're going to get our slope from. So we use the f of x at 10 and 9, and the x value at 10 and 9 to get the slope. Our left value, again, is 9, and the difference in x is 11 minus 9 to get the slope. That's how much the value increases from that f of x equals 9. And it looks like a pretty reasonable value. So we go from 8 to 9, we go from 75 to 80. From 9 to 10, we go from 80 to 99. So it's almost a difference of 20. So if we go from 10 to 11, it should be another difference of about 20. So 118 seems reasonable. It can be very dangerous, though, because a lot of times your model or your data is not valid beyond the points, the values you have for available data. It's especially true for noisy data. You can't necessarily extrapolate if the measurement value is bouncing around all over the place. So extrapolation is not a good idea in many cases, but sometimes you have to extrapolate a little bit beyond where you currently are. One of the issues you often run into, you go a little bit further and something happens in the biology or the thermodynamics. You can have, you heat water up a little bit more and it can turn into steam. Or if you change a condition, the biological sample goes into a different mode and dies or changes what it's doing significantly. Totally different qualitative examples. So you can't always extrapolate data, but sometimes you have to do it just a little bit. On the lower end, again, we could extrapolate down. Our left side is 1, our right side is x equals 2. So the x value in this case is going to be at 0.5. Use the x0, the left side. Get the slope again between the left side, the right side and the left side, the f of x on the right, f of x on the left. We get that slope, and we add it to f of x0. When we look at this data, going down from 2 to 1, we go down by what? 18. So going down another half, should be down another 9. And that's about right. So seems to make sense. And again, extrapolation is just not a good idea to do too often. Regression. Now, this is a technique that is developed for dealing with developing mathematical relationships. So you can look at a response variable that is governed by other forcing variables. So if you have values for x, something that forces a response. So in this case, it could be a linear regression where you know that f of x is a function of x. So you need to find b0 and b1. Or you could have lots of x values so that you know that the temperature is a function of the heating value and the sun's intensity, whatever. There's a bunch of different values that you want to put into a function. And if it's a linear form, you have these linear unknown model coefficients. Linear interpolation, linear regression only needs 2 values. For multiple linear regression, you can have an arbitrary number of linear terms, a constant, and other terms, and regress this value. You can have multiple linear regression. In this case, you have like one of your variables could be squared, but the coefficients still are linear. So all of the unknown terms b0, b1, b2, bn, in this case, are all linear coefficients, even if the value they're multiplied by are nonlinear. Now, here's an example of nonlinear regression. To find b1 and b2, these have a nonlinear relationship. So this is an example. If you can put it in the form a constant plus a constant times a variable plus a constant times a variable, then it's linear. Pretty much anything else is going to be nonlinear. So what do we do with that? We get a lot of data. We have a model form. If we have y equals something, a constant, plus a constant times x1, plus a constant times x2, plus a constant times x3, we can get lots of data values because we know x1 and we know x2 and we know x3. We run these experiments with holding x1 constant, x2 constant, x3 constant, and find the value for y. So we get an experiment, another experiment, another experiment, another experiment. We have 4 experiments. We have 4 unknowns. We write the model 4 times. And we set this up in a nice square matrix to solve for a0, a1, a2, a3. So this is an example of an ax equals b problem. However, when we have more data, there's something called the Moore-Penrose pseudo-inverse. So you can, if you have, instead of just 4 data points to solve for 4 model coefficients, if you had 4,000 data points, because we can take lots of data in some cases, we can have extra data, and this is what we call regression. You have more data points. You're trying to find the best model to fit all of that data. You set up the model the same way. You know the x values, you know the y values. You have these unknown model coefficients, but you have too many data points. Instead of just picking 4 of them, you get the best model that reconciles all of the data together. And you do that with a Moore-Penrose pseudo-inverse, which only requires some multiplication, A transpose A, the inverse of that matrix times A transpose times B. It's a little more complicated than the simple AX equals B, but this is a very powerful thing, and this is what Excel actually does when you plot data and you do a regression in Excel. So this simple formula is used to back out the linear coefficients for your model. The correlation coefficient is also important. So when you do a regression, it represents how good your model fits the data. So it gives you something to look at when you're modeling data. So a lot of times we record this r squared value. We don't typically do this by hand. So when you're in Excel, if you do a regression, you ask it for the r squared, and a 0.99 or 0.95 is a pretty good fit. But correlation does not imply causation. So you always have to be careful with data. Something may seem to correlate, but you can't always trust that, oh, we think that this is a function of this variable. Well, it may be, it may not be. It may just happen to correlate, and maybe both of them may be a function of some other variable that you haven't measured yet. So be careful with statistics, be careful with interpolation, and be very careful with extrapolation.